Hello, and welcome to the first in a series of 5 instructional videos where I'll show you how to fit reactor network models to tracer data using some software that I've developed in R. So if you're not here already, please come to my website, toolsforwater.com. And on this website, there are a number of different things that will be helpful to you in replicating some of the work that I've done. The first is the Fitting Tracer Data tab. This has a series of tutorial videos, this one included, on how you can perform this work, and it steps you through it one chunk of code at a time. Before we get started, you'll need the software R for statistical computing, RStudio, which is a helpful interface to run the code in, either some tracer data of your own or some example tracer data I'll show you shortly. And it also helps if you've downloaded the paper where this was accepted in the Journal of American Waterworks Association. So this is a peer-reviewed process that was come up with to fit these models to tracer data. If you go over to the code tab, you'll find 3 files. One is the reactor network model fit. This is the code I was referring to. And we've also got some example tracer data that I'll walk you through. And so if you download these 3 files and you save them all to the same folder, you'll be able to follow along. So I've done that already, and we'll start out in the tracer study file. And imagine we have a hypothetical reactor that's got a volume of 100,000 gallons. We have a flow coming into it of 1,000 gallons per minute. And to that flow, we inject a tracer. And at the outlet of that reactor, we measure a tracer. So if we've got a flow of 1,000 gallons a minute, a volume of 100,000 gallons, then our hydraulic residence time, average hydraulic residence time, will be V over Q, or 100 minutes. Let's assume we start injecting that tracer at 7 a.m. at a concentration of 1 milligrams per liter, and that we have some background concentration. So that background concentration is the average tracer concentration prior to the start of the tracer study. And imagine that every 5 minutes we're collecting a sample for this tracer and measuring its concentration, which is what you see right here. And this will go up and up over time until eventually we reach a concentration of 1.20 milligrams per liter, which is our background plus our tracer dose. And we can calculate the time elapsed since the tracer study started. And so we know that 7:05 is 5 minutes after the time that we initially injected the tracer. And so we've got time since the injection occurred, and we can also subtract out our background concentration of 0.2 milligrams per liter. Now this background tracer you might not have depending on what you use as a tracer. However, in the drinking water field, commonly we use fluoride, and it's important to separate out that background concentration. So once you have time elapsed and the background subtracted tracer concentration, we can then calculate the 2 parameters that this code will use. These are theta, which is equal to elapsed time divided by hydraulic residence time, and C over C naught, which is the observed tracer concentration divided by the injection concentration. So in this case, it's that average hydraulic residence time in the denominator and time elapsed in the numerator. And for C over C naught, that is, again, background subtracted concentration divided by the tracer inject concentration. So you can do the same thing with your tracer data. If you have a tracer that you've measured over time, you can take these same steps to get to the theta versus C over C naught stage. And you can copy and paste these as values into something that I'm going to call my tracer. You, of course, can call it whatever you like. And the important thing here is that we get the headings to be theta and C0. This is important because the code that I'm about to show you references these headings. And so it's important that this be theta and CC0. This is not the letter O, it's the number 0. And so make sure that you've got theta and CC0 as in C0, the initial concentration. And then the code will be able to work with whatever tracer data you have, provided that it's in this format.